Color has a strong psychological impact on people. It can change our mood and even our behavior. Imagine a world where everything is gray, with no bright signs, no colorful interiors, and no vivid objects. Most of us would find that environment dull and depressing. Paint and coatings are everywhere in daily life. Traffic signs, advertisements and billboards, paper, wood and metal surfaces, interior walls, furniture finishes such as varnishes, and industrial equipment. Beyond appearance, coatings protect materials, especially metals, from corrosion and weathering, extending the service life of products such as cars, ships, and machinery. In short, it is difficult to imagine modern life without coatings. They make our surroundings more attractive, and they provide essential protection for the materials we use every day.
In this session, I will begin with a short historical overview. It's interesting to see that humans have used pigments and coatings for thousands of years, which shows how deeply color and decoration are connected to human nature. Then we will look at the main ingredients of paints and what each ingredient does. This gives us a practical way to understand why different paints behave differently and why certain paints are better for specific applications. Understanding the molecular structure of alkyd resins help us to understand the drying mechanism of paints. Next, we will discuss what happens after paint is applied to a surface. In other words, how paint dries and becomes a solid film. A simple process flow diagram of paint manufacturing will be discussed, from weighing raw materials to mixing, milling, filtering, and packaging. Finally, I will briefly review the key properties used to evaluate paints and coatings. For further reading, a very good reference is the chapter titled Paints and Coatings in Ullmann's Encyclopedia of Industrial Chemistry.
Paint is part of a larger family called coatings. Coatings have a major economic and practical impact. They protect objects against the environment, for example by reducing corrosion, and they also improve appearance by providing color and surface finish. Evidence of early painting is remarkably old. Carbon-14 analysis of cave paintings suggests some are about 30,000 years old. This strongly indicates that the desire to color and decorate surfaces is a long-standing part of human history. Historical records also show coatings used in ancient furniture. For example, some items preserved from around 200 BC in China were coated with natural lacquer made from the secretion of the lacquer tree. Pigments were mixed into the lacquer to produce black or red finishes. Early oil-based paints used natural oils, such as linseed oil. These oils contain unsaturated bonds. When exposed to air, oxygen can react with those unsaturated sites and create cross-links between molecules, gradually converting the liquid oil into a solid film. In the early 1900s, alkyd chemistry became a major development. Alkyd resins were synthesized and later commercialized for coatings. They can be blended with natural oils such as soybean, linseed, safflower, and other unsaturated oils to produce durable, weather-resistant coatings. During and after World War II, there was also strong motivation to develop water-based paints using latex technology. In latex paints, polymer particles are dispersed in water rather than fully dissolved in an organic solvent. These paints generally dry quickly, are easier to work with, and reduce the release of volatile organic compounds. For many indoor applications, they are preferred. Today, the range of available paint colors and finishes is extremely large. Let us now look at what paints are made of.
Paint is a mixture of several ingredients, and each ingredient has a clear purpose. One of the most important is the binder. The binder is a polymer that holds all solid particles together and forms a continuous film after drying. In general, paint ingredients can be grouped into three main categories. 1. Binders and resins, polymers. 2. Pigments and extenders. And 3. Additives. Binders can be solvent-based or water-based. In solvent-based paints, the polymer is dissolved in an organic solvent. In water-based paints, the polymer is dispersed as fine particles, an emulsion, in water. Silicone alkyd resin is a hybrid paint binder made by modifying an alkyd resin with silicone, siloxane, segments. It forms the continuous film that holds pigment to the surface and gives durability.
high heat resistance, often used for heat-resistant and industrial coatings, better weathering, UV stability, and gloss retention than standard alkyds, improved water repellency and chemical resistance, typically good adhesion to metal and previously painted surfaces. Heat-resistant paints can be used for stoves, stacks, exhausts, and industrial maintenance coatings. Urethane paint was first created in the mid-1960s, utilizing the newly developed plastics technology of that era to be superior to enamel paint in terms of durability. It also has the advantage of being a surface that can be applied over enamel if the enamel-painted surface is prepared first. Urethane-painted surfaces are minimally affected by ultraviolet rays, making the paint a good choice for outdoor surfaces. It is widely used in the automotive industry because of its durability. Styrene alkyd resin is an alkyd modified with styrene to improve hardness, gloss, and drying speed, giving tougher, more water-resistant paint films. VT, or vinyl toluene, is an aromatic vinyl monomer, styrene-like, used to modify resins or coatings to increase hardness, gloss, drying speed, and water and chemical resistance. Two-component epoxy coating used as a maintenance finish for interior metal, concrete, brick, and masonry structures. Great shine, hardness, adherence, and endurance. Provides good resistance on severe environmental conditions and is recommended for coating tanks, pipes, machinery, and concrete floor surfaces that require excellent abrasion resistance, gloss protection, and film hardness. E50 must be used together with a polyurethane finishing when used on exteriors. Protects steel against corrosion created by spills, splashes, acid vapors, diluted alkalis, detergents, and solvents. A water-based binder is the film-forming polymer dispersed in water, latex or acrylic, vinyl acrylic, styrene acrylic. As water evaporates, particles coalesce and form a continuous film that binds pigment to the surface, providing adhesion, durability, and flexibility with low VOC. Pigments provide color and opacity. A common example is titanium dioxide, which is widely used as a white pigment because it is bright and has a high refractive index. Typical pigment particle sizes are on the order of a few hundred nanometers. Proper pigment quality and dispersion strongly affect hiding power, coverage, and appearance. As organic pigment widely used, we can list phthalo blue, PB 15.3, PB 15.6, is very strong tinting, transparent, intense green to red undertone blues, excellent light fastness, used for bright, clean blues and high chroma mixes. Ultramarine blue, PB29, is slightly violet-leaning, granulating, moderate tinting, very light-fast, ideal for skies, shadows, and natural, warm blue mixes. Indigo, traditionally a deep blue dye, often lower light fastness. In modern paints, it may be a different, more permanent pigment. Check the pigment code on the label. As inorganic pigment widely used, we can list red iron oxide, PR101. This is an opaque, earthy red. This has very high light fastness, and it has strong tinting. This is common in primers and masonry and industrial coatings. Yellow iron oxide, PY43. This is opaque to semi-opaque yellow, or ochre. It has excellent light fastness, and it's stable and economical. Black iron oxide, PBK11. This is opaque, slightly warm black, very stable, and it's used where durability and heat stability matter. Carbon black, PBK7. This has very strong tinting, a deep neutral to cool black. It has high UV absorption and can increase viscosity and reduce hiding if overloaded. Titanium dioxide, white, PW6. This has the highest hiding power and brightness, excellent opacity, and it's the primary white pigment in most paints, rutile grade common. Extenders are lower-cost solids such as calcium carbonate, silica, or clays. They can reduce cost, adjust texture, and influence mechanical properties. Additives are used in small amounts but can be critical. Examples include dispersants, wetting agents, biocides, anti-molding agents, anti-corrosion agents, and many others depending on the application. Finally, note that some coatings contain no solvent at all. Powder coating uses fine solid particles that are electrostatically deposited onto a surface and then cured by heating so the binder melts and forms a durable film. In this session, however, we will focus mainly on liquid paints. This table shows one example of a typical paint composition. The numbers vary by product, but the structure is common. A significant fraction is binder, along with pigments and extenders, and the remainder is solvent or water, plus small amounts of additives. Now, let us look more closely at one widely used binder family, alkyd resins. Alkyd resins are a large and important family of binders. Conceptually, an alkyd resin is based on a polyester backbone that is chemically modified with fatty acids. A common starting point is the formation of a polyester from a polyol and an acid anhydride. Glycerol is a well-known polyol because it contains multiple OH groups. Phthalate anhydride is a common anhydride because it provides carboxylic functionality. Through esterification reactions, ester bonds form between the OH groups of the polyol and the carboxylic groups of the anhydride. Repeating this reaction produces a polymer chain, a polyester. A key step is then the incorporation of fatty acids. The fatty acids used for alkyd resins are typically unsaturated, meaning they contain double bonds. Those unsaturated sites are important because they enable oxidative cross-linking during drying, which gradually hardens the coating film. After application, drying typically occurs through two main mechanisms. First, the solvent evaporates. This step is relatively fast and depends on factors such as coating thickness, airflow, temperature, and solvent volatility. Second, the binder film hardens through cross-linking. For many oil-based and alkyd systems, this is oxidative cross-linking. Oxygen from air must first diffuse into the coating film. This diffusion can be slow, especially for thicker coatings. After oxygen reaches the polymer, it reacts at unsaturated sites and forms crosslinks between polymer chains. As crosslinking progresses, the coating becomes harder and more resistant to scratching. This is why a paint surface may feel dry after a few hours, but it can take much longer to fully cure. In practice, catalysts known as dryers can accelerate oxidative curing. A familiar example is that a thin layer of natural oil left on a surface can slowly harden over time, and the same chemistry is used intentionally in many coating formulations. This slide shows a simplified process flow diagram for paint manufacturing. The goal is to combine solid and liquid ingredients and produce a stable paint with uniform color, controlled viscosity, and consistent performance. Step 1. Weighing and pre-mixing solids. Solid raw materials such as pigments, extenders, or fillers, and solid additives are fed to a weighing system. Each ingredient is measured accurately and then transferred to a premix tank or powder mixer. Step 2. Milling and dispersion, ball mill. After premixing, the solids are sent to a mill. A key purpose of milling is not only to reduce particle size, but also to break pigment agglomerates and achieve a uniform dispersion. Poor dispersion leads to low hiding power, unstable storage, and non-uniform color. A ball mill is one common milling device. It is a rotating cylindrical drum that is partially filled with grinding media, the balls, and the material to be milled. As the cylinder rotates, the balls are lifted and then fall or roll, creating impact and shear forces. These forces break down agglomerates and can reduce particle size. Inside the drum, the motion can be described as cascading and cataracting. At appropriate rotational speed, typically below the critical speed, the balls tumble and slide, generating strong mixing and grinding action. If the speed is too low, grinding is weak. If it is too high, the balls may be pinned to the wall by centrifugal force and grinding efficiency drops. Key operating variables include rotational speed as a fraction of critical speed, ball size distribution, ball to material ratio, residence time or batch time, solids concentration, dry or wet milling, and temperature control.
In paint manufacturing, milling is usually wet. The pigment and extenders are milled in the presence of part of the binder and solvent, or water, to form a concentrated dispersion. This helps prevent re-agglomeration and improve stability. Grinding media selection matters. Ceramic balls, such as alumina or zirconia, are often preferred because they reduce contamination compared to steel media. If slight wear occurs, the resulting fine ceramic particles are typically less problematic than metallic contamination for many paint applications. In this video, I am showing a 3D ball mill model provided by Ibrahim Zokai, and I would like to thank him for permitting its use. The model illustrates the rotating drum, the drive mechanism, and the feed and discharge. If we imagine the drum as transparent, we would see the balls moving through the powder or slurry, continuously mixing and grinding. Step 3, post-mixing and finishing. The milled dispersion leaves the mill and enters a buffer tank. It is then transferred to a finishing mixer where the remaining ingredients are added, such as plasticizers, catalysts or dryers, and additional solvent or water to reach the target viscosity. Step 4, screening, filling, and packaging. Finally, the paint is passed through a fine screen or filter to remove any remaining oversized particles. The finished paint is pumped to the filling machine, packaged into cans, labeled, and sent to storage as a marketable product.
To close this session, let us summarize the main properties used to evaluate paints. These properties depend strongly on the intended application. First, rheology is critical. If the paint is too thick, it cannot be applied properly. If it is too thin, it may drip, sag, or provide poor coverage. The user often adjusts viscosity by adding a controlled amount of solvent, depending on whether application is by brush, roller, or spray. Second, film performance after drying is essential. A good coating should adhere well, resist scratching, and maintain integrity over time without flaking. Third, for coatings used in wet environments, like swimming pools, boats, and ships, water absorption must be 0 or very low. Otherwise, moisture can cause blistering, flaking, and paint delamination. Appearance matters. Depending on the application, the desired finish may be glossy, semi-gloss, or flat. In some cases, transparent coatings are preferred, especially for wood, where we want to see the grain. Color and opacity are also major performance indicators, linked directly to pigment type and dispersion quality. As you may have noticed, fluorescent paint plays a major role in nighttime traffic safety by improving visibility and helping drivers detect signs and markings more quickly. Finally, durability in the service environment is critical. Some coatings must resist sunlight and UV radiation. Others must resist water, chemicals, or biological growth. For example, coatings for swimming pools or marine structures must resist water exposure and biofouling, and anti-corrosion performance is essential for many metal surfaces. I hope this session helped you understand the main ingredients of paints and why each ingredient is included. You should now be able to explain in simple language how a paint dries and how it is produced on an industrial scale. The next time you see a freshly painted surface, you may think about the two-stage drying process: first evaporation, then curing and cross-linking. Thank you very much for watching this session. I hope it helped you build a clear picture of the key concepts and how paint is produced from petrochemical products. Please continue with the next session on crude oil characteristics.